Hello, my friends of Hatari Labs. My name is Montoya. Please welcome to this tutorial. This tutorial, we are going to simulate some infiltration galleries. Okay, so here we have some infiltration galleries, and these galleries are below the a river. Okay, we're partially below a river because actually uh, on the, as you will see here, okay, there is a small part that is not below. Okay, so here you see that, and we are going to model and simulate the inflow to the galleries. Okay, so how much water is actually capturing the galleries, okay, divided in batteries. So this is gallery 1 and gallery 2, and we are going to do that based on MODFLOW on Voronoi mesh, based on a model built on MODFLOW6 and mf6Voronoi. Okay, so let's start. What we have here is the cross section. We have the infiltration galleries. We have the limit of the model. Okay, and then we have a regional flow that is a boundary conditions on the that represent the regional distribution of the water table. Okay, great. So let's start. I'm not going to close this. Okay, you are going to receive on the description of the video, you are going to receive this, that you have to extract here. So under your documents, you should have this folder that has this structure. Okay, with that, we start with Anaconda prompt cd documents, cd infiltration. Okay, and then here Jupyter Lab. Great. Okay, so, okay, what you are not going to receive is the model, the out, and the JSON. These are generated by the script, so I'm going to delete it, not to make you confused. Okay, okay, so the water table as well is a product. Okay, great, so, okay, so you're going to receive the executable, a project, a raster file with the elevation and the water table, the folder with the scripts, a chef file, and the BTK as well. You are not going to receive. Okay, great. So let's go to a script and let's say this as rename as P0. And what you are going to store here in P0, okay, in P0, what you are going to store is we are going to copy the templates. So we are going to list the templates. There are only 6 templates. We are going to use the generate Voronoi for steady state, model creation for steady state, and the VTK generation. Okay, so we are going to generate the Voronoi, but this will be for gallery. So the generate, and this creates this file that has a prefix of gallery. And then here we have the model creation as well for gallery. Okay, and then you have the BTK generation as well for gallery. Great, so here we have the 3 files. Okay, so let's start with the generation. So okay. So the project name will be Infiltration Galleries. Okay, the maximum refinement is 25. The multiplier is 1.5, and we have a model for the model limit. We have the galleries that will have a discretization of 1, so it's the minimum size. We have the river that will have a discretization of 5, and as well we have the regional flow that has a discretization of 1 as well, of 10, I guess. Okay, so we generate the galleries, and we are working with only 4,000 cells. Okay, but when you use the discretization of 1 meter, you might have these issues of short sights. Okay, when you have this issue of short sight, you have to check the quality of your Voronoi meshes. Okay, so here we have some issues, but we can fix those issues by uncommenting this and generating the Voronoi and check it again. Okay, and then when you see that your mesh has not edges shorter than your threshold, means that you have done well, and then you don't have any problem. Okay, okay, that you have fixed the mesh. Okay, so we are going to create the output folder and store the mesh there. Okay, and then we can open the and plot. Okay, so this is the mesh. Beautiful. Okay, and from the mesh we generate the JSON. Okay, okay, this is the JSON. So what it has been created is the JSON and the output folder. Okay, so let's go back to script. Now we have generated the Voronoi mesh. So let's go here to the model creation. On the model creation, we have to add 3 more cells because we need the multi-polygon, we need these tools, and they generate the raster. Okay, so we have this. So we have the DSV, the cell2D. Okay, the dem file is on the raster folder and is called dem44v2. Okay, this one. Okay, this is the dem file. So here we have 10 layers. Okay, so we are going to use 10 layers. While the first layers, it is our intention to have layers of around 1 meter, and the remaining layer will be thicker. Okay, great. So we can open here the model files, and as well this one. Here we are going to use 250. The discretization. Okay, on the KX we are going to have 2 Ks. Okay, the first one is for the first 5 layers, that is 4 10 to the minus 4, and for the remaining layers will be 5 10 to the minus 6, and for the first 2 layers can be convertible, while the rest are confined. Okay, and here on K, on the Z direction, will have an isotropy, so it's NP array of Kx divided by 10. On the storage, well, it's a steady state. On the recharge, there is a recharge and evapotranspiration. Why not? Okay, So let's see. On the chef file, so we have the river, okay. And the river is only one river, one polygon, but we are going to create one multi-polygon. Why we are going to create? Just in case that you have more polygons, okay, so it will be defined as river as well, okay, but in this case, okay, it's only polygons. So these are the river cells. There is a problem here. Polygons. This is polygons. Right. So now let's create. Okay, in the template, the river acts as a drain, but in this case, we are going to use it as a river. So, uh, so it will be the surface, the river surface, the water surface will be at 0.3 below the model top, and the bottom is okay is at 0.6. In this way, the river is only defined on layer one. Mhm. Okay, yeah, great. Okay, so let's see, since there are more cells here. Okay, so now we are going to work with the regional boundary condition. So on the regional flow, we are going to apply this elevation. That is why we use the get late cell elevation to perform raster. Okay, and these are the cells. Okay, so these are on layer 2 in this case, okay, with this value and this conductance, and this will be assigned as general head boundary, okay, and then we can plot it on the first. These are the cells defined as general head boundary on the border, okay. They are not exactly on the border, okay. We can fix that by moving this line closer to the border, okay. But what is intention is that you have a head here that actually represent the general behavior of flow. So that is why this is needed, and the change won't have that impact, okay. So next, what we are going to do is we are going to work with the drain package. Okay, so and then we are going to use bound names because we want to extract the amount of water that flows into the galleries. Okay, for this we use another that is get late cell elevation to perform elevation. So this is the elevation of the gallery, and this is the infiltration gallery 1 and the infiltration gallery 2. Okay, so here we have gallery 1, gallery 2, and okay, so these are the cells. So these are, for example, the cells of gallery 1. And okay, so and then we define our drain package. Okay, we define the drain package, but as well we create a drain dig where the gallery 1 will, okay, will have a column that is going to gallery 1, will store the drain, okay, the flow out, flow in, will flow out only. Okay, and we initialize this observation. Okay, and then we, okay, so that is uh, what we initialize, and then we plot our drain for the layer 5. Okay, so these are the drains already on the cells. Okay, we can do a cross section. Okay, so we can do a cross section, and in this cross section we have the river, and then these are the cells of the drain. These are the cells of the drain of the infiltration galleries. Great. Okay, so we run the simulation. Let's see if that everybody runs. Ah, okay, the initial head. Okay, the initial head, maybe we haven't run that cell. We might have not run that cell. Uh, okay, we haven't run that cell. Okay, so that is why I'm going to go to this line, kernel run up to selected cells because I want to run till this point. Okay, it's running with 250 iterations. Great, normal termination. Let's go here to model files. Let's go to the list file, and it has reached convergence, and the percent discrepancy is 2.2. Interesting. Okay, so we got the heads, and then we can plot the heads, but with just 10. Okay, so this is the heads at layer 4. Interesting. But now we can plot a cross section. Okay. And okay, so here we see the impact, but on this part, actually the we see the that the water table is decreasing. Okay, but this is because this part is under the river, and the river fixes the elevation, or at least tries to fix, while here this part is not under the river, so it's actually can have an impact on the water table. Okay, great. So, and finally we export the water table. Okay, amazing. So can we see the flow on the to the to the galleries? Yes. Why? Because here we have the gallery one, that is this one, and the flow to the gallery one is 15 liters per second doing the conversion, and the flow to the gallery 2 is 47 liters per second. Okay, great. And okay, so let's see here. Let's go and create the VT case. Let's go here to the gallery VTK generation. Okay, so I'm going to open the model files. Okay, great. We are going to initialize the VTK. We list the model, we load the model, we get the head, the parameter, the boundary conditions, the head VTK, and the water table. Okay, so that means that in the oh 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 okay, it has created here under the scripts. Okay, okay, it has created, no, not really under scripts. Where it has let me check again. Yeah, because okay, this is point. Okay, great. Let's kernel run all cells. because it has to be created. So it hasn't created. Okay, now it creates the VTK, and in this VTK we have the evapotranspiration, the parameters, and other the recharge, okay, and the drain and so. Okay, so it has finished create. So let's go to Paraview. Okay, and let's go to documents. Let's go to the VTK folder. For example, we have the drains, and the drains are the infiltration galleries. Okay, so these are the infiltration galleries. Okay, so we have as well the river. Okay, so this is the river. And what else do we have? We have the water table. So there is the water table. Okay, so this is the water table. And this is the part where where there is an impact on the water table, but there is no river, so actually that is why there is an impact on the water table. Okay, so that it will be uh, the results of this tutorial. That is quite interesting. I hope that you find it useful. My recommendation is that you follow all the steps, and then based on that you apply that to your own projects. Okay, all the files in the description of the video, just to remind that we are Hatari Labs, a platform for knowledge sharing. So we have a lot of courses uh, in our e-learning platform. Okay, here and as well in our shop. Okay, great. And courses and diplomas. And then if you want to support us, and because we spend a lot of resources in our research, you can support us in Patreon as well. Okay, please have a great day, and que viva el software libre.